Namaste, Shubhodayam, good morning to all the students and other participants. Welcome to this second session of the training program, Semiconductor Exposure Training, with a special emphasis on VLSI. Just to give a quick recap of what we discussed yesterday, I introduced you to the VLSI design engineering economics aspect. We also talked about what are the different types of ASICs that are possible. We talked about full custom ASIC, standard cell based ASIC, as well as gate array based ASICs. And I also said that going forward we will talk mostly about cell based ASICs, also called CBICs. Today, continuing with the discussion, I plan to cover the differences between an FPGA and an ASIC. We also discussed yesterday about when an ASIC can be manufactured, what are the economic aspects of manufacturing an ASIC. Today we will talk about the differences between an FPGA and ASIC, and then we will also have a look at the simple manufacturing steps of an IC, how an IC is made, how the layers are printed one on top of the other, and later on we will also look at an NMOS characteristics or the device characteristics for an NMOS transistor. So let's get along. Just a little bit of an overlap with whatever we have done yesterday is that yesterday we discussed about the types of ASIC. I also mentioned here that ASICs are made on a thin circular wafer, and each wafer holds hundreds of dies or device, and when they are manufactured they get cut into several laser cut into different chips, or they separate out. The transistors and the wiring are made from several layers built on top of one another, each layer separated from the other by an insulating layer. The first few layers define the CMOS devices, and the remaining layers are used for making the metal interconnections between the devices. This is what we meant. Then I also talked about full custom ASICs. I mentioned about the full custom ASICs where the transistors and everything is customized right down to the device level. Then we have standard cell based ASICs, also called CBICs, and gate array based ASICs where you have basically an array of gates, and then the interconnections need to be made, but these are not very really popular in the current days. The full custom ASICs, I mentioned about the full custom ASICs. I'm just putting them once again over here for a quick recap. Then we talked about standard cell based ASICs, or CBICs as they are called. The advantages are that it uses a standard cell library in which the cells are pre-characterized and pre-tested. So what the designer needs to do is to only pick up the cells from this characterized library and pre-tested library, and then use them and place them on the silicon for getting the for sending it for manufacturing. The masks define the interconnections, which define the interconnections are basically customized, and these are pre-tested and pre-characterized. This is the one which is defined by the user. Gate arrays basics are not so popular, not so prevalent in the current days, and I mentioned yesterday that we are not going to dwell upon these particular type of ASICs. Okay, now today is the fresh part of the discussion. This was just a quick recap of where we left off. It's like a relay race, you know, when one person hands over the baton to the other one keeps running, and there is an area of overlap. So it's like that. So I just had a quick glimpse of whatever we discussed towards the end of yesterday's session. I will give you the differences now between ASIC and FPGA. It is important to understand this because an FPGA is also an ASIC, kind of an ASIC, but we will look at this. An ASIC specifically, as the name implies, is an application specific integrated circuit. For all those who are not very familiar with what ASIC stands for, it is designed for one sole means single, one single purpose, and it keeps functioning the same way throughout the whole operating life. It functions the same throughout its whole operating life. For example, the CPU inside a telephone. Inside a telephone you will have a CPU, and a CPU inside the telephone, or the processor, a microcontroller inside a washing machine. They are all examples of ASIC. They have a fixed function and they execute that function time and again, over and over and over again. The logic function of an ASIC cannot be changed to anything else, because the digital circuitry which is there inside the ASIC is made up of permanently connected, or what is also known as hardwired logic cells. Logic cells, when I say logic cells, it is not only meant or confined to gates. Logic cells is basically the lowest level of cell that is available in the library, and it may consist of gates, flip-flops, counters, multiplexers, so on and so forth, okay, and then in silicon. So basically the digital circuitry is hardwired, and therefore it cannot change its function. On the other hand, we have FPGA, standing for Field Programmable Gate Array. Field Programmable Gate Array. It is an integrated circuit which can be field programmed. A field program doesn't mean that you go into the field and program it, or agricultural field or any other football field or cricket field. No, that's not the meaning of that. Field program means to be able to program it by the end user, where the actual point of deployment takes place, where the FPGA is actually being used. There it can be programmed and to work as per the intended design. So a design is done. In an ASIC, the design gets manufactured, whereas in the FPGA, it doesn't get manufactured. It just gets programmed into the FPGA. You have to put that design into the FPGA, and that FPGA will work as per the intended design. This means that an integrated circuit which can be field programmed, okay, it means that this FPGA can either work as a microprocessor, or it can work as an encryption unit, or a graphics processor, a graphics card, or a graphics processor, or even all these three at once. A part of it can work as a MUPI, a part of it can work as a graphics unit. Okay, technically that is possible. FPGA working as a microprocessor can be reprogrammed to work as a graphics card also. That means if you have a single FPGA, that FPGA can be used to test or to verify the functionality of a microprocessor. It can be used to implement a graphics unit. It can be used as a network controller, or it can be used as any other logical functional unit. It can be reprogrammed. And there is also one field of computing called reconfigurable computing, wherein dynamically, that means when the FPGA is working itself, at that time itself, a part of the FPGA can be reprogrammed to function as some other unit. Reconfigurable computing. Hello, I think I'm getting a call. Hello? Hello?
Hello?
Yes?
Hello, sir. I'm audible, sir?
Yes, you are audible. Good morning. Tell me, what is your question?
Good morning, sir. My name is Mahendranath. I completed my BTech in NIT Srinagar in ECE. I'm a 2019 passed out student, sir.
Okay.
So now I want to enter VLSI field, sir. It's already 2 years. Now I have applied for VEDA IIT, sir. So it will take another 6 months to complete the training. So will it affect my job opportunities, sir? It is already 2.5 years.
Yeah, as I mentioned, we'll do one thing. We will have a 15-minute discussion at the beginning of the second session today, okay, wherein many of the questions which the students have posed will be answered in a discussion between me and between the director of VEDA. He will be here, and then we will answer those questions about job opportunities and all that. We will put all those questions into one place so that we will be able to smoothly proceed with the discussion. Okay? Is that right? Is that okay?
Sir, so I should call in the next session, sir.
No, you don't. You may not need to call. There will be a discussion in which the job opportunities and how people can apply to VEDA, and how the students can get trained in VLSI. All these things will be discussed.
So please answer this question also, sir, that it will be already 2.5 years, sir, so it will affect any job opportunities for him because it is late.
Sure, that will be discussed. That will be discussed.
Yeah.
Thank you, Mr.
Thank you.
Mahendranath. Thank you.
Yeah.
Let's proceed. So, therefore, an FPGA, I was talking about reconfigurable computing, in which while the FPGA is in action, is working in the circuit, it can be part of the FPGA, can be reconfigured to function as some other unit. Okay. So that's the essential difference between ASIC and FPGA, but we'll get into more details through this tabular comparison between FPGA and an ASIC. FPGA is a reconfigurable circuit. They can be configured with a different design. Every time you reprogram an FPGA, it can take up a different design. So an FPGA can be, as I said, it can be a processor, it can be an encryption unit, a graphics unit, it can be anything. Whereas an ASIC is a permanent circuitry. Once the application specific circuitry is taped out, tape out is basically the process in which the final design file goes for manufacturing. That is what is meant by tape out. Okay. Once it is taped out into silicon, the functionality, the circuitry cannot be changed. It is permanently hardwired. Okay. The second point of comparison is that design is specified using hardware description languages, about which we will talk a little later. HDL they call hardware description languages, such as Verilog or VHDL. Don't think that VHDL stands for Verilog HDL. No, VHDL is a short form for very high speed integrated circuit. This is very high speed, VHSIC, hardware description language. That is VHDL. Okay. For FPGAs also it is pretty much the same, and you do the design using Verilog and VHDL. FPGAs are not really suited for use in high volume mass production, in the sense that if you want to sell a product in which a particular functionality, a large functionality is to be embedded, is to be contained, then that FPGA is not a suitable part for use in that particular product, because FPGAs have got a lot more logic, a lot more circuitry, a lot more number of interconnect resources, okay, than are actually required by the function. So therefore, unless if the function itself is whatever function we want to implement, if it is in high volume, then FPGAs are not suitable, because FPGAs are power hungry, they are more expensive than ASICs, and therefore if the sales of your particular product is limited to a few thousand or tens of thousands, then possibly you can go for FPGA. But if the sales of your product are going to go into millions of units, FPGA is definitely not a suitable part for use in that particular product. ASICs are suitable for high volume mass production because they consume less power. ASICs, FPGAs are less energy efficient. They require more power for the same function, which ASICs can achieve much more easily. Okay. The power consumption, because you have dedicated circuitry on an ASIC, and therefore there is no extra circuitry, no extra fat, no extra resources which will consume unnecessary energy, and therefore this is useful. I'm getting a call, so let's take this call here. Hello?
Hello?
Yes? Hello? Please ask the question.
Sound is not audible, sir.
Sound is not audible? Hello?
Hello, sir.
Am I being heard? Am I audible to you?
In the line.
No, I think you're not being heard. I'm not hearing you properly. So there might be some technical difficulty, not very sure. But we will proceed once this technical difficulty is overcome, or once things get right, then we will take your question.
sound is not and it's difficult to understand that I have.
We will continue. Okay. So FPGAs is limited in terms of its operating frequency compared to ASICs of similar process node. Process node means similar technology. The reason for this is that the amount of logic and the amount of routing resources that are present in the FPGA are so many compared to what is really required that the interconnect lengths are long because you have more logic than what is required, and FPGA is an already manufactured part. You are putting the design inside an FPGA, an already manufactured part. Therefore, the routing resources consume a lot of delay in terms of the interconnect delays, okay, and therefore FPGAs are limited in their operating frequency compared to ASICs of a similar technology, whereas ASICs can operate at much higher frequencies. However, when you want to change your applications, okay, and reconfigure an FPGA very frequently, then FPGAs are useful. They are highly suited for applications such as radars, cell phone based stations, etc., where the current design might need to be upgraded to a better algorithm or to a better design at a later point of time. Okay, so then ASICs are definitely not suited for application areas where the design might need to be upgraded frequently or even once in a while, because ASICs, you cannot change the functionality of an ASIC. You cannot upgrade an ASIC to a better algorithm simply by changing a few lines of code in the design. No, you'll have to go through the whole process of manufacturing once again, which is very, very expensive. And the last one of the last slides is that FPGAs are preferred for prototyping. What happens is when you are developing an ASIC and you want to go in for a manufacture of an ASIC, one of the first things that most of the organizations do is that they use an FPGA for verifying the functionality of that ASIC. So while we are comparing FPGA with ASIC, okay, we are saying that FPGA is used for verifying the functionality of an ASIC in silicon. Mind you, verifying the functionality can be in simulation or it could be in silicon. Okay. Putting the design in FPGA means that you are verifying this particular design in FPGA. The ASIC design is getting implemented and is getting implemented in FPGA and is being verified there for its functionality. It may not work at the required speed, that's okay, but still the functionality is being verified in silicon. Whereas ASIC, you don't verify an ASIC by making an ASIC. Okay. ASIC making is not recommended to prototype a design using ASIC unless it has been absolutely validated. One important thing is FPGA designers, okay, people who are designing logic circuits which have the objective of ultimately going into an FPGA, such designers really don't need to worry about the physical design aspects or the physical back-end aspects of the design. Every ASIC design has got two aspects. One is the front end, the other is the back end. So the back end, that means the physical design, the layout and all that, it doesn't need to be bothered about. The designers really don't need to bother about this, because the resources in an FPGA are already laid out. You only have to define the interconnections. And that is, moreover, FPGA does not require any DFT related kind of stuff to be included in the design, because the design has already been fabricated inside an FPGA. Now, the FPGA is already a fabricated unit, and while manufacturing the FPGA, people who design the FPGA should have taken care of the DFT aspects. The person who is doing a functional design which is going to get implemented in the FPGA really doesn't need to worry about the DFT or the physical design aspects. Whereas ASIC designers, here again, okay, this is what I was saying. There was a little bit of a delay in the slide arriving, but that's okay. ASIC designers need to care for everything from RTL down to the reset tree, the clock tree synthesis, the physical layout, routing, all these design for manufacturing, everything needs to be taken care of. Now, all these aspects would have also been taken care for FPGA when the FPGA was getting manufactured. However, as an end user, you are not manufacturing the FPGA. You're using the FPGA for putting your design, for implementing your design inside that particular chip. So these are the ideas of the comparison between FPGA and ASIC. Now let's see how are the costs involved. The costs involved, if you look at this, the total cost, okay, ASIC initial costs are very, very high because you need to, as I said yesterday, the cost for the development, the non-recurring engineering costs, the recurring costs, and the fixed costs, all these costs, okay, add up to a huge value for the ASIC for low volumes. Okay, whereas FPGA you really don't need to worry about this. Simply buy an FPGA and use it. Okay, but as the number of units keeps on increasing, the FPGA cost is linearly proportional and has got a greater slope than the costs which increase for the ASIC, okay, when the ASIC volumes are increased. And the point of crossover is the point where the costs due to the FPGA usage and the costs due to the ASIC usage are the same. Beyond this volume, the ASIC usage will give you lesser costs. It will be cheaper to manufacture an ASIC, whereas under this volume, this is the crossover volume, under this volume it's always better to use an FPGA, because let's say your volumes are somewhere on this line, somewhere over here, then obviously it doesn't make sense for you to go in for an ASIC, because the ASIC is going to be much more expensive, almost twice as expensive as the FPGA when you use an FPGA. With the advancement in technology, okay, and the manufacturing processes as they change, maybe this graph also may change slightly, but by and large it gives you an idea that low volumes FPGA is better, high volumes ASIC is better, because you can get a better profit from ASICs, okay, in this area, and you can get a better profit from FPGAs in this area. Let's talk about VLSI technology. Many people say the people are very crazy, I'll tell you. Engineers say, I'm working on 3 nanometers, I'm working on 5 nanometers, and they want to say that I'm working on as low a number as possible. Who knows, tomorrow they will say that I'm working on -5 nanometers. It might so happen that technology might advance in such a way that you might say that one day like this, we never know. So what does this number indicate? What it meant previously was basically the technology was basically the distance between the drain and the source in an NMOS transistor, an NMOS device, or a PMOS device for that matter. Okay, the distance between the drain and the source, that is, what is that? That is nothing but the channel length. We will come to that. I'll run through the NMOS characteristics a little later in this or the next session, but we will come to that. So all of you who don't know how a NMOS device looks like, I will draw a figure and we will go into some details of that aspect. The distance between the drain and the source is also the channel length. Today what it means is may not necessarily mean the distance between the drain and the source, and the smallest feature size that can be processed on silicon. For example, many years ago in the 1980s or early 2000, let's say 90 nanometers, 130 nanometers. 130 nanometers is nothing but 0.13 microns, because a micron is 10 to the power of -6 meters, a nanometer is 10 to the power of -9 meters. Okay. Let's take a call. I'm getting a call. Hello. Yeah, the call got cut. We'll proceed further. Okay. So today it means the smallest feature size that can be processed. The smallest feature size that can be processed may not necessarily mean. And today, if Samsung says that they are working, this is a 7 nanometers technology, the 7 nanometers technology of Samsung and the 7 nanometers technology of let's say Intel may not always give the same transistor size. the 7 nanometers technology. So today it means different things for different manufacturers. It's not necessarily the same thing. Intel may say 7 nanometers, its transistor size might be something. Samsung, Motorola, it might say 7 nanometers, or maybe Micron technology for memories. Its transistor size might be something different. Okay, this is what it is today. Then technology is steadily advancing. What do you mean by advancing technology? Advancing technology means a shrinking size of the transistor. Shrinking or scaling. How does it help? It helps because it provides a capability of having more transistors on a particular silicon area. By doing that, more transistors means obviously more functionality. And when more functionality comes into a particular chip, you have lesser number of chips on a particular board. Lesser number of chips means lesser interconnections, lesser soldering, lesser possibility of loose connections, lesser possibility of dry solders. Okay, all these things, lesser possibility. Take a call. I'm getting a call. Hello.
Hello.
Yes, can you be a little louder?
Hello, sir. I am Srijna.
Yes.
Am I audible, sir?
Yes, you are. You please ask your question.
Sir, so microcontrollers which we commonly use, in which category do they come under? ASIC or an FPGA?
No, microcontrollers is an ASIC. It's not an FPGA, because microcontroller, although it can be programmed, it is software programmed. Okay, it executes a program. Okay, it executes a program. The software runs on microcontroller, but the microcontroller itself cannot be classified as an FPGA, because you cannot use the microcontroller in any other way at all. Okay, does that answer your question? One more question is coming. We'll take up that question, please. Yes, please ask your question.
Sir, am I audible?
Yes, you are audible.
Sir, regarding EDA tools, many people say that many of the EDA tools are already automated, and in coming future, they are being to be completely automated. So, what is the role of the physical engineer going to be in future? If the tools are going to be completely automated, then what we can do?
Well, the tools are not automated. Many a times the process is automated. Tools are there which automate the process. Yes, of course it is there, but the physical design engineer, there is a scope for physical design engineer. I do not know many years down the line what will be, but in the immediate foreseeable future, the physical design engineer will make use of these tools. The tools are automating the process, yes. But at the same time, the technology is also advancing. So I personally, I don't see any so-called threat to the physical design engineers' job positions in the immediate foreseeable future. Okay. Yeah. So let's proceed. So when we have more functionality on the particular chip, obviously lesser interconnections on the board means lesser chances of dry solder, loose contacts and everything. Therefore, it increases the reliability. Also, when we go in for advanced technology with shrinking size of the transistor becoming smaller, it operates at a higher speed. But obviously, the moment we say that it operates at higher speed, obviously the power, the dynamic power in ASICs or ICs is kind of linearly proportional to the operating frequency. Therefore, the more the frequency, the higher the speed, the more is the power. In addition, what happens is, once the transistors scale down to a smaller size, the drain and the source come closer and closer to each other, and this increases the leakage power. We'll see what is meant by leakage power in the next few slides when we talk about the transistor characteristics. Okay, moving forward, The challenge is in very deep submicron technologies. Deep submicron technology is basically technologies which are smaller than, previously they used to say smaller than 0.25 microns. Deep submicron is up to 0.25 microns. Smaller than that, that is 130 nanometers, 90 nanometers, 45 nanometers. Now people are talking about 2 or 3 nanometers. Okay, 7 nanometers is something which is becoming more or less available commercially. 13 nanometers is like commercially available now. So what are the challenges in these particular very deep submicron technology? As I said, I may not go into the exact lower level details of all these points, because from the point of view of understanding, okay, it is important to simplify and put across the point in a simplified manner to make the students understand the overall at the top level, rather than go into every detail of each this thing. Depth is not something that I'm planning to go into right now. So the limitations, there are limitations of normal or planar MOS transistors, which led to the use of what is known as a FinFET as the MOS device. Most of the current transistors actually use current products use FinFET. I'm getting a call, so please allow me to take this call. Hello.
Yeah, hello.
Yes, please ask your question.
Hello.
Yeah, go ahead.
Yeah, sir, why we are using PMOS and NMOS for creating CMOS?
Why we are?
Why we are using PMOS and NMOS for building CMOS?
CMOS stands for complementary. PMOS and NMOS. We will see later why PMOS and NMOS are used. Why not only NMOS? Or why not only PMOS?
NMOS and PMOS only.
Because MOS, metal oxide semiconductor, why we are using CMOS? One of the main advantages is basically the density. Density can be extremely large for devices. Second thing is the power consumption compared to bipolar devices is much lower in CMOS devices. Why do you use PMOS and NMOS? I will answer this question shortly. Why not only NMOS or why not only PMOS? Okay? Yeah. So FinFET is not a planar device. We can call it as a three-dimensional device. It's not a planar device. And the advantage of having a FinFET is that the FinFET has lower leakage power. Leakage power is the power consumed by the device when it is not switching. Either when the output is at logic 1 or the output is at logic 0. When it is not switching, at that time the power consumed by the device is a leakage power. The FinFET provides a lower leakage power and better control of electrical fields inside the device, because the planar transistor, as it shrinks, becomes smaller and smaller. There are what are known as fringe effects in the electric field. You must know what is meant by an electric field. Electric field is basically the voltage per unit distance. So that electric field has got fringes. It is no longer properly well defined electric field, and therefore the FinFET gives you the advantage of providing a better control for the electric field. A better electric field is more properly controlled in the FinFET. And because of leakage, lower leakage power, a FinFET can also be operated at higher speeds. Because of the better electric control, better control of electric fields, and both these factors contribute to a higher operating speeds for the FinFET. Let's see, this might not show you much, but the chips have grown basically as per the Moore's law. I can tell you that this Intel 4004 over here, some of you who are observing this on the TV may not be able to read this properly, because I have picked up this figure. This is not a figure that I have made, this figure that I have just taken. This is your Intel 4004. Your Pentium comes somewhere over here. These three are your Pentiums over here. And then finally here you have the last one over here is the Apple A12 Bionic processor. Just before that is the Snapdragon 835, which goes into most of your Android phones. This is Snapdragon 835 is from Qualcomm, this processor. Okay, Snapdragon 835. So this is how the chips have grown. This is the year 1970 early 70s, where the Intel 4004 was created or was developed, and this is the year around 2020, 2019, 2020, where this is there. And the transistor count, if you look at this here, it is between 1 billion and 10 billion. Billion is 10 to the power of 9, not million. Million is 10 to the power of 6, billion is 10 to the power of 9. Okay, so as I said yesterday, Xilinx's latest offering of FPGA contains 37 billion devices on it. 37 billion, 37 into 10 to the power of 9 devices. Such a massive scale of integration is possible today with the technology. I'm not very sure. I think that particular technology is a 12 nanometer technology using FinFETs. Let's move on. The chip density has increased primarily due to scaling. Okay. Now, scaling is a term which is used in different ways, but one of the simplest ways of defining what scaling is to reduce the area of every transistor by using a lower feature size. Feature size means the length between the drain and the source gets reduced, the area of the gate is reduced, the thickness of the oxide also gets reduced. Okay, all these things reduces the area of the transistor. Therefore, once the area of the transistor is reduced, for a given area of silicon, you can put more devices, you can have more functionality. Lower feature size leads to lower supply voltage. Obviously, it must be like that. As you decrease the feature size, for example, if you decrease the distance between the drain and the source, then the electric field in between the drain and the source becomes larger and larger. Getting a phone call. Let me take a call, please. Hello.
Hello, good morning, sir.
Good morning.
Sir, in FPGA we are using the SDL languages, Verilog and VHDL.
Yes.
But in ASIC, which language we are using?
We are using Verilog and HDL, Verilog, VHDL, system Verilog. Everything can be used for design. I mentioned there that ASIC and FPGA, when the design is being done with the intention of either manufacturing that design or putting that design in an FPGA, Verilog or VHDL or system Verilog can be used. These are the most popular languages, or some of the people prefer to use other languages also, like system C and all that, but typically Verilog and VHDL are used.
What purpose we are using Mentor graphics?
What is the thing? What is the question?
Mentor graphics, sir.
Mentor Graphics is an EDA tool company now acquired by Siemens.
Okay, sir. Sir,
Mentor Graphics is not a language. Mentor Graphics is a company. Okay, Verilog, VHDL and the system Verilog are the three most popular languages as far as design is concerned for either ASICs or FPGAs, both. Okay. So let's continue. I think the call got cut. The lower feature size leads to lower supply voltage, and that is required, lower supply voltage, because if you keep the same supply voltage of, let's say, 5 volts or 3 volts and then keep decreasing the size, the distance between the source and the drain, then the electric field prevalent inside, or which is existing in between the drain and the source, becomes large, because electric field is nothing but the voltage difference between the drain and the source divided by the distance between the drain and the source. Therefore, if this distance gets reduced, the electric field increases, and that may cause a rupture inside the device with such high electric fields of having megavolts per centimeter, which is very high electric field. So this leads to higher switching also, frequency, because switching speed increases. How is the switching speed increasing? Because when the distance between the drain and the source, I will also tell you how to identify the drain and how to identify the source. Many people don't know how to do that. Okay. When the distance between the drain and the source decreases, then the time required for the carriers, that is the electrons in the case of an NMOS device, to commute to go between the source and the drain, to travel between the source and the drain, decreases. Okay, and when that decreases, obviously the switching speed increases, because the execution is basically depending upon the switching execution frequency depends upon the switching speed, and when that switching speed increases, the frequency also decreases, the frequency increases. What are the disadvantages of shrinking? Of course, it leads to higher power. Of course, when you shrink, you add more devices, and therefore you work at a higher frequency, and therefore the power also tends to increase. Although individually transistors may have smaller power, dynamic power, but the leakage power is more. Okay, overall it tends to increase the frequency. Therefore, these days there is a lot of work going on towards making power decrease in the VLSI circuits. Low power VLSI designs are gaining momentum, and many of the chips have got low power features incorporated into the design. One of the most simplest low power feature to be incorporated in any VLSI design is clock gating. You switch off the clock to some portion of the circuitry which is not being used, and therefore reduce the power in that particular area of the circuitry, because every time you switch a particular node, power gets consumed. Why does power get consumed when you switch a node? We will see that through diagrams a little later in the day today. Also, as drain and the source come together, come closer together, then there is a higher leakage current also that exists, and therefore the power tends to increase as you keep shrinking the devices, and this challenge has to be addressed, and it has to be overcome. To understand scaling, we must look at the MOS transistor and its fabrication. I will go through a simple example of how an inverter can be fabricated. Of course, this is an isolated picture of an inverter. Don't think that an inverter is fabricated as a separate part. No, only a part of the ASIC, which actually is basically the inverter, that we will see starting from a substrate, how it will go through. So basically here are these manufacturing steps identified or given in 3 or 4 different slides. First, we have a P substrate. Okay. On a P substrate, NMOS devices are manufactured. For manufacturing PMOS devices, it would have required an N substrate. However, we cannot take 2 different substrates and manufacture devices on 2 different substrates. We take only a P substrate, and therefore then try to make N devices on P devices by having an N well on some P substrate. So when this substrate is taken, and it is taken through a process of CMP, chemical mechanical polishing, the surface is polished, and then it is heated in an oxygen rich environment at about 1200 degrees centigrade, which gives you a layer of silicon dioxide, SiO2, as you can see over here. Then the photoresist is applied, and the wafer is spun at high speed. It's spun at high speed, it rotated at high speed, so that this particular photoresist, which is basically a liquid, gets evenly distributed in a thin way on the surface of the substrate. Okay. Then through a mask, in which a window is there in a mask, this is exposed to ultraviolet radiation, in which what happens is that which is exposed to ultraviolet radiation, maybe that which is not exposed to, which gets softened out, and then it is removed by means of some chemical. Typically that chemical is hydrofluoric acid, HFL. Okay, and some other mixture is there. Okay, so this is what happens. Then after that is done, the silicon dioxide also is washed out. This silicon dioxide, which is over here, that is also washed out by a chemical. Once that is washed out, okay, because this photoresist has hardened, and it prevents this silicon dioxide from being washed out. Once this silicon dioxide is washed out, then the top layer photoresist is also washed out. The photoresist is washed out, and then an N well is made. The first few steps of manufacturing are basically to incorporate or to fabricate the PMOS transistors, because we cannot first make an N-well for one place. The N-wells, wherever the N-wells are required on the entire wafer, okay, those N-wells need to be made on the entire wafer with the objective of later on making PMOS transistors. So therefore this is done, this N-well is done. The thickness of this wafer is typically 0.4 mm or about 400 microns. It's about 400 microns. Let me take a call. Hello, good morning.
Hello, sir.
Yes.
This is Anis, sir.
Yeah, Anil, tell me.
Sir, can we integrate your inductance in FPGA?
No, typically inductances are not printed in ASIC, in silicon. Inductance capacitances can be printed, but these capacitances will be very, very small. Inductances are used, if at all you want an inductance, it is used outside of the chip in the circuit.
And what about any audio codecs? Like if something has an analog ground, can it be integrated in FPGA? Because FPGA
these days, yes, these days FPGAs do contain analog circuitry also. Yes.
Sir, how is logic blocks are manufactured, sir?
Logic,
like with any copper tracks or?
Logic blocks are manufactured means the whole ASIC is manufactured.
That is in FPGA, sir. How are logic blocks are connected?
FPGA is basically a chip which has been manufactured in which there are programmable interconnects as well as programmable logic devices. Okay, the programmable interconnects are long interconnects are there, short interconnects are there, and basically aluminum is used as the metal for material for interconnection. That is, the metal interconnects are made from aluminum, though research is going on to convert or to change from aluminum to more suitable material from the point of view of interconnect resistances and delays. Okay, copper technology is being worked on, but right now aluminum is the most prevalent or the most widely used metal.
Sir, I have one more question also.
Yes.
Because from the Ohm's law we can say R equals to rho L by as the length increases, the resistance also increases.
Yes.
And here the interconnects are so long, right? So the resistance also matters when we manufacture a FPGA, right? How will overcome that resistance? Right?
Exactly. The resistances are long enough. Yes, they are long. But then for clocking purposes, you have special routing tracks with low resistances and low delays. The more the resistance, the greater is the delay.
Yes.
The more the resistance, the greater is the delay, obviously. If you if you're looking at the thing, maybe I can show you how I'll just go into this and show you. If you have an interconnect resistance like this, okay, and obviously you will have some parasitic capacitance over here, okay, and when a particular node switches over here from 0 to 1 or 1 to 0, this node will not switch unless the capacitance charges, and the capacitance charges like this exponentially. Okay, therefore the amount of time it takes from this point onwards to this point onward, this is your interconnect delay. The more the resistance, the greater is your RC time constant. RC time constant tau is equal to RC. Okay, so this is what causes the FPGA to have greater delays, and therefore this is what prevents the FPGA from working at as high a frequency as the ASIC. You are right, FPGAs don't work at as high frequency as ASICs, because they have got much more extra interconnect resources, logical resources, which may not be used by all the designs. Let's move on. Okay, so the N-well, this N-well is dug, and I was mentioning about the thickness of this particular wafer, the substrate. This is maybe about 0.4 mm or about 400 microns, and this N-well can be anywhere from 40 to 80 microns typically. Okay, and therefore once this N-well is done, this N-well gives the feeling of an N substrate inside which PMOS transistor can be made. Therefore, everywhere that PMOS transistors are going to be made on a particular chip, such N-wells are made as the first step. Okay. Then after the N-well has been made, again this silicon dioxide is washed out, and thus you are left with a P substrate with an N-well. This N-well can be made by either a process of diffusion or a process of ion implantation. There are two ways in which it can be done, and of course the N-well, there will be some lateral spread towards the left and towards the right also. Therefore, you may say that why this is like this and N-well is moving like this. Once they move inside, okay, they go and penetrate into this N-well by some the donor materials like phosphorus and arsenic. Okay, they are N-type materials. Okay, call. Yes. Hello.
Hello.
Yes, please ask your question.
Hello.
Yeah, I'm listening. Hello.
Hello, sir.
Yes, please go ahead, ask your question.
Sir, this is VLSI, sir.
What was the question? I didn't understand your question.
Sir, VLSI సంబంధించి sir ఇది.
Yes.
Sir, how many days, sir, training?
Oh, come on. Really,
Huh?
this will be for 2 weeks, but this was not the type of question I expected you to ask. Okay, it's all right. It's for 2 weeks.
2 weeks, sir.
Yes.
Sir, which channel, sir? Which channel this is?
TSAT. T for Telangana, SAT. Okay, we'll move on. So this N-well is now, this substrate with the N-well is now ready to receive and make P transistors, so that what happens is now a polysilicon is deposited on top of this gate oxide, which was prevalent in the earlier slide over here. Okay, now this is there. Now again, this thin layer of gate oxide, this one more time a gate oxide is put over here. That thin light blue line that you area that you see there is the thin gate oxide, which is put on top of that. On top of that, polycrystalline silicon is there. Okay, now this polycrystalline silicon, underneath of that is the gate oxide, that the whole thing is then masked, is exposed to a mask, and once again it is washed out, okay, using chemicals. I'm not going into every process of detail of this, what chemicals are used and what are the things that are used, but this particular thing tells you that there is a polycrystalline area over here and there is a polycrystalline area over here. So these, okay, there's a little bit of a delay in the slide arriving. So when we have this, we have a gate formation under this and we have a gate formation under this. This thin silicon dioxide is the gate oxide. Now once this is done, the P regions, this is again coated with a thing, with an oxide. We have the donors as phosphorus and arsenic. Donor materials are phosphorus and arsenic, the N-type donors. N-type materials are called donors, and the P-type, which make the P-type things, are called acceptors. Okay. Then once you look at this, okay, this is available. From here, now what happens is a contact is made here, N plus contact inside the N well, and N plus contact is made, and all N plus wells are kind of made in this particular step. Over here an N plus well is made. Now you may ask, why are you making an N plus well inside an N well? I will come to that. Okay, here two N plus wells are made, and these N plus wells now form the source and the drain. In a CMOS device or an NMOS device, the source and the drain are perfectly interchangeable, okay, because they are identically constructed. Okay. Now this N plus contact is made over here, and at all such places where PMOS transistors have to be made, it is made parallelly across the entire chip. It is made, and therefore we see this particular thing. Now this N plus is made in this step. I will come to why this N plus well is made over here. Then we make this P plus contacts. This P plus contacts define a PMOS transistor over here, and this P plus contact on a P-type substrate Let me take a call. Hello?
Hello,
Yes?
am I audible, sir?
You are audible. Please go ahead and ask your question.
I'm Naveen, sir.
Naveen,
What
yeah.
happens for the transistor size approximately equals to the electron size?
What?
In transistor size are reducing day by day. So when the transistor size is equal to electron size,
Oh, transistor size. I don't think transistor size will go to the electron size. No. Okay, electrons are far, far too small for a transistor size to achieve that dimension. Okay, at least not in the immediate foreseeable future. Okay. Yeah, let's proceed. So then the next steps are putting a P plus contact everywhere on the particular wafer. The idea is this P plus contact is for this P substrate, and this N plus contact or N plus well is in the N well. Then that defines two transistors. This is your NMOS transistor and this is your PMOS transistor. Okay, and after that what is done is then the next steps are followed. I have cut down on some of these steps, and ultimately what is done is this is basically an oxide over here, okay, which is deposited as an insulating material. This is a thick field oxide. You may not be able to see because I have taken this picture from a particular place, so the text was small. This is thick field oxide, okay, and later on this you can see that this p-type substrate, this forms the N transistor and this forms your P transistor inside the N well. Therefore the P transistor gets the feeling that it has been constructed on an N substrate, and the N-type transistor obviously is being constructed on the P substrate. Now this particular thing is metal. All that blue hatched portion that you see over here is a metal which actually connects to this P plus junction over here and this N plus contact point over here. Now these two are connected together by this particular metal. You can see that this terminal of the N transistor is connected to this terminal of the P transistor. This forms these two drains. This is the drain of the P transistor and this is also the drain of the N transistor. They are connected together. The reason for having this contact as N plus, that means more heavily doped than this particular N well, is that this, otherwise if this N well is directly connected to the metal, it will form a Schottky diode junction and it will not form an ohmic contact. The ohmic contact is required in order for the resistance to be the same in both directions of the flow of current, whatever current might be flowing. So that gives you an ohmic contact at this point with an N plus well over here, and it gives an ohmic contact at this point with a P plus well over here. So these are required to form ohmic contacts, so that this metal contact, this P substrate, is connected to this metal contact through an ohmic junction, not a diodic junction. This is how the two transistors will be fabricated and connected like this. Now just to end this session over here, you see that this first one, the light blue one over here, all this over here is silicon dioxide. Okay, this gray thing is N plus diffusion. This and this is N plus diffusion. This dark blue is P plus diffusion. This is polysilicon. Where is that polysilicon? This is a polysilicon and this is a polysilicon. Previously this used to be metal, but now it is polysilicon, and this is your metal. This is the circuit of an inverter, and I have shown you how an inverter is gets manufactured as a part of the overall ASIC. We have come to the end of our session right now. What we will do is we will take a break of about 15 minutes, and I will continue in the next session. In the next session, at the beginning, we will have a small discussion about how, and we'll take certain questions from students and also have a discussion on how students can get entry into the VLSI field. For right now, we will stop here. We will meet you on the other side of the break. Thank you for being with me. Thanks. Namaste.